Hello guys, up till now what we have covered in combinational circuits is we have looked at few of the arithmetic circuits that perform addition and subtraction operation, and we have also come across a device called the comparator which compares two binary numbers which may be single bit numbers as well as multi-bit numbers. So today we are gonna look at some other circuits. One such circuit is called as multiplexer. Here multiplexer, what it means is it basically works as a switch. So it connects multiple input to a single output. Okay, multiple inputs can be connected to a single output based on these control or select lines. These are also called as select lines because these lines are used to select which input must be connected to the output. These are those inputs. Okay, so there are two types of input. One is called as data input, other is called as control input or select input. Select input selects which data input should be connected to the output. Okay, these are the control lines or the select lines. So now where does it come in use is multiplexing can basically be used in telephone connections or telephone lines. Okay, suppose if there are n users, then there are possibly n into n minus 1 by 2 connections. These many connections can be possible, but we cannot keep a new line for each and every connection. Suppose each and every day many users are getting added on our telephone network, so we cannot lay down lines each and every day because such number of lines will not be feasible. And anyways, suppose I am talking to you, then that doesn't mean I'll be talking to you the entire day. Let us say I talk to you for half an hour. Then for the rest 23.5 hours that line will sit idle. So that is an inefficient use of the resources. What I can do is when I am finished talking to you, I can allocate that line to some other group of users so that they can also use that line, and that way number of lines that are required will be lesser. So if number of lines required will be lesser, my cost will be lesser and there will be more efficient utilization of my resource. So what we tend to do is we tend to connect a switch. As soon as you disconnect the call, that line will be allocated to some other group of users. That is called as multiplexing. That is multiple users making use of a single resource. So that is called as multiplexing. It has most of the applications in terms of communication. So here we will connect multiple inputs to a single output. So in general case, if there are n select lines, then generally 2 raised to the power n data lines are there and 1 output. The naming of multiplexer is on the basis of data lines and output, so it will be 2 raised to the power n is to 1 mux. Okay, so n select line, 2 raised to the power n data lines and 1 output lines. So here n is equal to 2, so 4 data lines and 1 output line, hence 4 is to 1 multiplexer. That means 4 input is to 1 output. Okay, so you may have gotten the basic concept of the multiplexer. Now you know. So let us look at some of the multiplexers. Like multiplexers can be 2 is to 1, 4 is to 1, 8 is to 1, 16 is to 1. So we'll be looking at some of the multiplexers to know how this circuit or how this functionality can be achieved in a digital circuit. So let us first start with 2 is to 1 multiplexer. So a 2 is to 1 multiplexer basically functions like a switch. This switch can be controlled by the signal S. So when S is 0, it is connected to I0, and when S is 1, it is connected to I1. This is how we can represent it using black box. Black box means functionality is hidden from me. I don't know the functionality or the implementation. I just know the inputs and the outputs. I don't know how is it working on the inside or how is it being implemented using various logic gates. And generally we represent multiplexer using this trapezoid. Instead of a square or rectangle, trapezoid representation is used. This is how we represent. Here data inputs are there, here select inputs, and here output lines. So this is how we can represent our multiplexer. So if we try and form the truth table for this multiplexer, then S0 and y. When S0 is 0, y is connected to I0. When S0 is 1, y is connected to I1. So this is the minterm 0, this is minterm 1. So y will be equal to, here S0 is 0, so S0 bar output should be I0. When S0 is 1, output should be I1. Now if you substitute here S0 is 1, then S0 bar will be 0. So y will be equal to I1. Similar way, when S0 is 1, S0 bar is 0, y will be equal to I0. So this is my logic implementation or logic expression for the 2:1 multiplexer. Now let us see how a digital circuit can be formed around this logical expression. So if you see here, I have taken S bar here and I have taken S here. So output of this AND gate will be SI1, S bar I0. So y will be S bar I0 plus S I1. This is my output. Always remember, S is equal to 0 corresponds to I0, S is equal to 1 corresponds to I1. Okay. So minterm 0 corresponds to I0, minterm 1 corresponds to I1. This is how we can implement a 2:1 multiplexer. But in reality, what happens is only 2 users won't be there. There will be multiple, let us say 8, 16, 32, 64. These sort of users will be there. So we need to perform a higher order multiplexer. So let us move on to the next higher order, that is called as 4:1 mux. Here we have 2 select lines. So 2 raised to the power n is equal to 4 data lines and 1 input. So here 2 select lines S1 and S0, then output y. There can be 4 combinations 0 0, 0 1, 1 0 and 1 1. So when 0 0, output will be connected to I0. When 0 1, output will be connected to I1. When 1 0, output will be connected to I2, and when 1 1, output will be connected to I3. So do remember the subscript beneath the input is same as minterms, because this is minterm 0, 1, 2, 3. So y will be, minterm 0 will be S0, S1 bar, S0 bar. When this minterm will come, y will be equal to I0 plus, when minterm 1 will come, S1 bar, S0, output should be equal to I1. When minterm 2 will come, that is S1, S0 bar, output will be equal to I2, plus when minterm 3 will come, S1, S0, output will be equal to I3. This is how we can implement a 4:1 multiplexer. Okay. So the main problem or the main challenge here is to build a higher order mux using a lower order mux. Now suppose I give you a problem that you have to design a 4:1 multiplexer using a 2:1 multiplexer. Then what you need to do is you need to design a circuit something like this. So here in this both multiplexer, S0 is the select line, here S1 is the select line. So let us try and design the truth table for this circuit. S1, S0, Y. Okay, 0 0, 0 1, 1 0, 1 1. Okay. So suppose S0 is 0 and S1 is 0. Since S0 is 0, this multiplexer output will be which one? First input. So that is I0. Okay. Since S0 is 0, which output will be there? I2. But S1 is also 0. Then the output will be first one, that is I0. So it will be I0. Now suppose S0 is 0, S0 is 1 and S1 is 0. Since S0 is 1, output coming here will be second one, this I1. S0 is 1, here it will be I3. But S1 is 0, so it will only take first output, that is I1. So it will be I1. Now we have taken S0 is equal to 1, sorry, S0 is equal to 0 and S1 is equal to 1. Since S0 is 0, I0 will come, I0. From here I2 will come, I2. And y will be equal to, since S1 is 1, y will be equal to second I2. Now if suppose S0 is 1 and S1 is also 1, then S0 is 1, that means I1 and I3. S1 is 1, that means I3 will propagate, that means I3. So this is my 4:1 multiplexer. Then how to identify how many number of multiplexers are required while designing? Just do something like this. Divide 4 by 2. That is 4:1, 2:1. So it will give you 2 as the quotient. Then divide 2 by 2, the quotient. It will be 1. Then add both of this. It is equal to 3 mux. That means 2 mux are at the first stage and 1 multiplexer at the second stage. So total of 3 multiplexers are required. Similarly, if I want to design a general procedure, let us say I want to design 16:1 mux using 2:1 mux. Then what you will do? You will take 16 by 2 plus quotient will be 8, 8 by 2 plus quotient will be 4, 4 by 2 plus 2 by 2. So it will be 8 plus 4 plus 2 plus 1. So it will be 8, 4, 12, 15. So if you see, for 16:1 mux, 15 are required, and for 4:1 mux, 3 are required. So what I can say, for a 2 raised to the power n is to 1 mux, how many multiplexers are required? 2 raised to the power n minus 1 mux are, which ones? 2:1 mux are required. Okay. So just a simple expression, I can write it down. So do remember this technique. How do we find the number of lower order multiplexers required to implement a higher order mux? So this is how we can implement that. For 2:1, the expression simplifies to 2 raised to the power n minus 1. Okay. Next, suppose I want to implement a 16:1 mux using a 4:1 mux. Okay. So what we do is, the higher order select lines, that is S3 and S2, will be used at a second stage. Okay. And the lower order select lines S1 and S0 will be used at first stage. S1 and S0 will be used as first stage, S2 and S3 will be used at second stage. And each stage will have the same set of select lines. Here there are 4 multiplexers in first stage, 1 in second. So it will have all same set of select lines, that is S1 and S0. So all 4 have S1 and S0. Then the inputs will vary for all the multiplexers. They can be written sequentially, like I0 to I15. They can be written in the same order. So now how did I identify how many multiplexers to be used in each stages? Divide 16 by 4, because 16:1 to implemented using 4:1. The quotient will be 4. Then divide 4 by 4. So it will be 4 plus 1, 5, 4:1 mux. Okay, so 5 multiplexers are required. It indicates 4 are in first stage, 1 is in second stage. So we require 5 4:1 multiplexers. 4 will be connected in first stage and 1 will be connected in the second stage. So general procedure, let us take a few more example. Suppose I want to design 64:1 mux using 4:1 mux. So what you will do is 64 by 4, quotient will be 16, 16 by 4, quotient will be 4, 4 by 4. So it will be 16 plus 4 plus 1, that is 21 mux. Similarly, if I design 64:1 mux, let us say using 8:1 mux, then what will happen? 64 by 8 plus 8 by 8, that is 8 plus 1, 9 mux. But what happens if I decide 16:1 mux using 8:1 mux? Then you will do 16 by 8, but now the quotient 2 is not divisible by 8. That means it cannot be designed using 8:1 mux. It will require 8:1 mux plus 2:1 mux. Then only I can design it. Okay, otherwise I will not be able to design 16:1 multiplexer using only 8:1 multiplexer. So every time the quotient should be a integer value, and that to a positive integer. If it is a fraction or if it is not divisible, then that means this multiplexer cannot be implemented using given lower order multiplexer. That is an impossible task. Now my multiplexer can perform or can implement a variety of logic functions. So if it can perform a logic functions, a variety of logic functions, then that means it must be able to implement logic gates also, because those are the most simple logic function. So we will see how multiplexer can be used as a universal gate. Suppose, first of all, remember the equation for 2:1. A bar I naught plus A I1. This will be my equation that I will be using. So if I take here, y will be equal to A bar into 1 plus A into 0. That is A bar. So it is equal to NOT gate or inverter. Now suppose if I take the second case, here y will be equal to A bar into 0 plus A into B. So it will be equal to AB. So which is an example of a AND gate. Okay. So here I can implement AND gate using a multiplexer. Now if I implement third one, y will be equal to A bar into 1 plus A into B. So it will be equal to A into B bar, A bar plus A B bar. Now this A is a redundant term, so I can write it like this: A bar plus B bar, and by De Morgan's law it is equal to AB bar, which is a NAND gate. Okay, so it can be implemented. NAND gate can also be implemented using a 2:1 multiplexer. Now let us see if OR gate can also be implemented. Suppose I am giving you this. So try to identify yourself also. If you calculate yourself, then it would be better. It will be A bar B plus A into 1. So it will be A plus A bar B. Now I know this term is redundant, so it will be A plus B. So it is a OR gate. If I take this, y is equal to A bar B bar plus A into 0. So it will be equal to A bar B bar, which is equal to A plus B bar. So it is a NOR gate. If you see between OR and NOR, just I have complemented all the inputs. B has converted to B bar, 1 is converted to 0. That is how we can convert a OR gate to a NOR gate. Same case was here between AND and NAND, 0 1 B B bar. Just the inputs have been complemented, and that way we can implement two gates of opposite nature. Here if I try to find this, can you guys also try it? Y is equal to what it will be? A bar B plus then A into B bar. So it is an example of XOR gate. So if I come to next, it will be y is equal to A bar B bar plus A B. So it will be a XNOR gate. If you see here also, I have just complemented the data inputs. Okay, nothing more. Now let us see some problems, what kind of problems can be asked in gate examination based on multiplexers, because multiplexers is one of the most important topic for gate examination. So guys, better you try it out yourself first of all. Let me know what is the y. Y will be, first I naught will be A bar B bar I naught plus A bar B I1 plus A B bar I2 plus AB I3. So A bar B bar I naught is equal to C bar plus A bar B C bar plus A B bar C plus A B C. If you take A bar C bar common from first two terms, it will be B plus B bar. If I take AC common here, it will be B plus B bar. So it will be AC plus A bar C bar, because B plus B bar will be 1. So it will be A X nor C. This will be my logic expression. So if you remember the logic expression for 2:1 mux and 4:1 mux, then I feel you can derive any logic expression using the multiplexer. But what if the question is asked in reverse? That is, I have been given the logic expression, I have been asked to implement that logic expression using the multiplexer. So let us see how we can do that also. So suppose these minterms have been given f a b c, and let us say we have to use AB as the select line, so that we can use 4:1 mux. Okay. So AB can have 4 combinations: A bar, B bar, A bar B, AB, and AB bar. Okay. And C can have 2 values, C and C bar. Or let us say C bar and C. So if all are complement, this will be 0th minterm. If it is A bar B C bar, it is second. If it is A B C bar, it is which one? 6th. If it is A B bar C bar, it is 4. If it is A bar B bar C, it is 1. If it is A bar B C, it is 3. If it is A B C, it is 7. If it is A B bar C, then it is 5. So these are the minterms that are there. And which ones are 1? 1, 2, 3, 5, 6, 7. Okay, 1, 2, 3, 5, 6, 7. Here it is 0. Here it is 0. So if you see here, A bar B bar, for this minterm, the expression will be same as C. If C is 0, then it is 0. If C is 1, it is 1. Here for A bar B, both values are 1. For AB, again both values are 1. For AB bar, it is again equal to C. Because if C is 0, output is 0. If C is 1, output is 1. So how it will be? Y. We know select lines will be AB. So A bar B bar means I naught. I naught is equal to C. I1 is equal to 1. 1 C. This is I naught, I1. This was equal to, sorry, I3 and I2. So that means this will be equal to C. Sorry, this will be equal to C, and this will be equal to 1. So I naught, I1, I3 and I2. Okay, I just written them in gray code fashion or the K-map fashion. So that is why these were shuffled up. Now let us change this select line. What about if I ask you the select lines should be, let us say BC. BC is my select line. Okay. So if BC is the select line, 4 possible combination: B bar C bar, then B bar C, then BC bar, then BC. Here A bar and A. A bar B bar C bar will give you 0th minterm. That means 0. A bar B bar C 1. A bar B C bar 2. A bar B C 3. A B C bar 4. 5. Then 6. Then 7. Okay. So if you see 1, 2, 3, 5, 6, 7. 1, 2, 3, 5, 6, 7. Here it will be 0, 0. Okay. So this will be 0. Here both are 1. So 1. Both are 1, 1, 1. So it will be I naught is 0. I1 is 1. I2 is 1. I3 is also 1. So we can draw something like this. Y. Here select lines will be BC and inputs will be 0, 1, 1, 1. Okay. So here A will not appear. Now let us take the last combination, in which we will take AC as select line. So if we take AC, A bar, C bar, A bar, C, A, C bar and AC, here it will be B bar and B. Now for A bar, B bar, C bar, it will be 0. A bar, B bar, C, it will be 1. A, B bar, C bar, it will be 4. Then A, B bar, C, it will be 5. Then A bar, C bar, B, it will be 2. A bar, B, C, it will be 3. A, B, C bar, it will be 6. Then A, B, C, it will be 7. So if I mark ones, 1, 2, 3, 5, 6, 7. Here it will be zeros. So this is coming out same as B. This is 1. Then this is B. Then this is 1. So it will be Y. Here A and C. Here it will be B1, B1. This is how we can implement the logic. So this is how you can implement any logic using the multiplexer. Just form the truth table or find out the output for each combination of the select lines. Just then you can easily implement it. So if we try to summarize, what we have learnt is, from any 2 is to power n is to 1 multiplexer, we can implement any n variable Boolean function. Okay? So n variable can be implemented using 2 raised to the power n is to 1. But if you want to implement n plus 1 order function, like we did in this example, we took 4 is to 1 multiplexer and we implemented 3 variable functions. N plus 1 variable logic, then we require inverter also, because sometime it may arise that B bar may be coming or A bar may be coming. Then we require inverter plus multiplexer. If inverter is coming, then we can realize any n plus 1 variable logic. If inverter is not there, we can realize n variable Boolean logic and maybe some of the n plus 1 variable Boolean logic, but not all. Like in this case, without any inverter, I was able to implement the 3 variable logic, but it may not be true in all the cases. So do remember, we need to get an inverter in order to implement all n plus 1 variable logic with a 2 raised to power n is to 1 multiplexer. So in the next class, we will be looking at one more such circuit which is very important for GATE exam and practical applications also. Till then, try to implement some of the random logics that you create by yourself using the multiplexer. That will benefit you immensely.